started the discussion about moment of inertia. So we will continue from that point, and today's lecture will discuss more about calculation of moment of inertia by integration. So this is a very important aspect of mechanics, this entire chapter of rotational mechanics or rigid body mechanics. Okay, so what we learned last time is that when a rigid body is in pure rotation, the kinetic energy of such a body is given by the formula half I omega square. This is the kinetic energy for a rigid body in pure rotation, where I is the quantity called moment of inertia. Which is basically the rotational inertia with respect to the axis of rotation. So, and of course, omega is the instantaneous angular speed. In this moment of inertia is given by the formula integration r squared dm, where r is the perpendicular distance for mass dm with respect to the axis of rotation. So this is how we define the moment of inertia for a rigid body with respect to a particular axis of rotation. So to that end, we had seen a couple of standard formulae last time. Moment of inertia of a thin uniform rod with respect to its center of mass axis, we had seen was ml square by 12, and with respect to an axis at one end of it, we had seen was ml square by 3. So this kind of thin uniform rod, if the axis of rotation was the perpendicular bisector, then moment of inertia was given by ml square by 12. Whereas the same thing, if the axis is passing through one end of the rod, then we had seen moment of inertia is ml square by 3. But of course, m is the mass of the rod and L is the total length of the rod. So these two are absolutely standard formulae which you have to memorize. These two formulae of moment of inertia, as well as you have to be comfortable understanding the derivation process which was done by integration. So similar kind of principles and guidelines are used for integration here, as we have done for center of mass. So generally, when you are calculating moment of inertia by integration, you keep in mind the guidelines that dm can be taken as a length element, it can be taken as a surface element, it can be taken as a volume element, depending on whether the shape of the body is linear or the distribution of mass is linear or two-dimensional or over a surface or over a three-dimensional volume. So this is the same concept that we had seen in center of mass chapter. So we take length element lambda dl for dm when the mass is distributed over length. Or it's a linear distribution of mass. We take surface element when mass is distributed over a surface. And we take volume element rho dv when it is distributed over a three-dimensional volume. Okay, so let us understand some more examples.
Sir,
Yes, sorry for the interruption. Let's look at the next example of moment of inertia. So next, again, another standard formula will derive. Moment of inertia, we'll just give a short form MI for moment of inertia for a thin uniform ring. So the first case of this we'll discuss is if we take the axis being the symmetry axis, that is the axis through its center and perpendicular to its plane, that kind of symmetry axis. So when we take this axis, it's one of the simplest examples of moment of inertia, because we are talking about a thin ring like this, let's say, whose mass is m and radius is r. Now we're talking about an axis which is the axis through the center and perpendicular to the plane. So that is, the rotation is happening like this. So if you visualize this three-dimensionally, we are talking about the ring being like this and the axis being like this, perpendicular to its plane and passing through its center. So that's why this becomes very easy, because now you take any sectional mass dm. You take a section which is of mass dm. It is at a distance of capital R. So moment of inertia, which is integration r square dm, just becomes integration capital R square dm for all the particles. So it's just r square into the total mass. So that's why this is the simplest derivation of moment of inertia. When we have a thin uniform ring rotating about its symmetry axis, every particle dm of that ring is actually having the same distance from the axis, which is capital R. So that integration r square dm just becomes integration capital R square dm, which becomes nothing but total mass into capital R square. Okay. So simple, but nonetheless, this is an important formula to remember. So moment of inertia of a thin uniform ring about its symmetry axis. Okay. Remember, whenever we talk about moment of inertia, we have to specify what is the axis of rotation we are talking about. So for this particular axis of rotation, this is the moment of inertia.
Sir, can you explain again?
Sorry, can I?
Sir, can you explain again?
Yeah, the ring is rotating about the symmetry axis, as you can see, and any particle on its surface, on its circumference dm, is at a distance of how much from the axis? Capital R, no? So moment of inertia, just substitute in the formula integration r square dm. What is the value of r over here? R's value is equal to capital R, which is the radius of the ring for all the particles. So it's like there's nothing further to explain in this system. Capital R is a constant, no? So it comes out for the integration.
Sir, so here we don't have to use dm equals to lambda dl.
Sorry, come again.
Sir, so here you have to not use dm equals to lambda dl.
So you can use, but uska fayda kya hoga? Because anyway, it is just integration of dm only now. So integration of dm, whether we divide it into lambda dl and then take the lambda outside and integrate dl, or we just leave it this way, that is nothing but the total mass. So no further step is required. You understanding?
Yes, sir.
Because you know dm is not accompanied with anything else. Na? Capital R square is a constant. It's come out. We don't need to write it as anything else. It's just this integration dm is just a total mass. You can write it further like this. You can write integration dm as integration lambda dl. Okay, so that will become integration m upon 2 pi r into integration dl. So this is again a constant m upon 2 pi r. Integration dl is nothing but the total length. So it will be m by 2 pi r into 2 pi r. Okay. So this step is unnecessary over here. So it's because you anyway know that this is nothing but the total mass. So it should be m.
Yes, sir.
Okay. Now in the next example we will see of this, you will see that we can't do this because it's very rare that we can take the whole thing outside and we are just left with integration dm. So the second case of this is when we take a different axis. We'll take the axis as the diameter axis next. Diameter of the ring. So now if you visualize the same ring is rotating in this way, it's rotating about an axis which is lying in its plane and divides it into two equal halves, bisects it in its plane. This is the axis of rotation. This axis. So you know, as it is spinning, look like it's going around about this axis like this. So that kind of situation. So now, if we take an arbitrary particle and an arbitrary position like this, you can see that its perpendicular distance is no longer capital R. Okay. If the ring's mass is m and radius is capital R, this distance is R. But what about the perpendicular distance from the axis of rotation? This is a perpendicular distance. So this is our small r. So if we take this angle as theta, we can see that for a particle at a position theta, okay, the small r is equal to how much? It is capital R cos theta. You can see in this triangle, it's the base. Okay. So now we have to use that integration method, that we have to take a differential element here whose thickness is dl and it's an arc, so it is itself it is subtending a small angle d theta. So that particle dm, its mass will be lambda dl. Now lambda here will be m upon 2 pi r, total mass upon circumference, and dl will be how much? It will be r d theta. So further, dm, which is lambda dl, will be written as m upon 2 pi r into r d theta, or dm can be substituted as m by 2 pi into d theta. There's something you're already familiar with this method in this thing, in center of mass. Okay. So now moment of inertia of that small particle is r square dm. So r is r cos theta and dm is m by 2 by d theta. So moment of inertia of that whole ring becomes integration of this for all the particles. So it becomes integration r square dm or integration m upon 2 pi capital R square cos square theta d theta. Now you can see I'm covering all the particles so over a circle. So theta should go from 0 to 360 degrees or 2 pi. So this is the integration that I'm left with now. So mr square by 2 pi into integration cos square theta d theta from theta equal to 0 to theta equal to 2 pi. So just write it down up to here, and I want you people to do the integration yourself now. Okay. I'll just remind you what is the method of doing integration of cos square theta or integration of sine square theta. We use the trick that cos square theta can be expressed as what? 1 plus cos 2 theta by 2, or sine square theta can be expressed as 1 minus cos 2 theta by 2. Okay. So this is a method we use for doing this kind of an integration. You use the formula that cos 2 theta is equal to 2 cos square theta minus 1, or 1 minus 2 sine square theta. So this trigonometric identity is used in doing these kind of integrations. So just try to work out the integration yourself. We will discuss the final answer then.
Yes, sir.
Okay, so let's complete the integration here. So we can write this cos square theta as cos 2 theta plus 1. So now this cos 2 theta's integration will become sine 2 theta by 2. So there's already a by 2, so it will become by 4. And then you have 1 by 2 terms, so it will be theta by 2. Now on that you put the limits theta equal to 0 to theta equal to 2 pi. So when you put the limits, you can see that sine theta term will just give us 0 minus 0, whereas this will give us 2 pi by 2 minus 0. So you get pi inside. So this moment of inertia will become mr square by 2. So moment of inertia of a thin ring about the diameter axis, now we can see by integration, the formula comes out to be mr square by 2. So it's equally important to remember the direct formula for application in questions, as well as understand the derivation process from integration. So this is another standard formula that you have to memorize. Okay, so hope this was clear. Now let's move on to the next example. Now we move to from linear mass distributions to surface mass distribution. So our next example is going to be a two-dimensional distribution of mass. So thin uniform disk. mass and radius r. Now we will take the axis as the axis passing through the center. So when we take the top view of this, can you imagine the axis coming out of the plane of the diagram through the center perpendicularly? This is the axis of rotation. So to find the moment of inertia, what we can do is we can make use of our previous formula that we just derived. If we slice this into thin rings, of radius r and some small thickness dr, so if we take a thin ring like this, of radius r and thickness dr, so the mass of that ring will become sigma into dA. So this is a surface distribution of mass. And it's a uniform thin disk. So sigma is nothing but total mass upon area. So this will become sigma upon pi capital R square. But area of that thin ring will become circumference into thickness. So this will have an area dA equal to circumference multiplied by the thickness, 2 pi r dr. So dm can be written as sigma upon r square. So m upon r square. Here also it should be m. This will become 2m upon capital R square into r dr. So this is what we'll substitute as the mass of that thin ring. So this thin ring that we mentally sliced out from the disk, it is having a mass of so much. Just note down up to here first. Okay, so now let us see, once we have understood the mass of this ring, then this thin ring itself, it has a moment of inertia which is dm into r square, because we all just saw previously that moment of inertia of a ring of mass capital M and radius capital R was mr square. So now we have a thin ring of mass dm and radius small r. So its moment of inertia will be dm into r square. So substituting this value of dm, you can see that the ring's moment of inertia will be given by this formula. Okay? Just multiplying dm with r square. So this is the moment of inertia of the thin ring. So moment of inertia of the disk will come by integrating the moment of inertia of all these thin rings. So it's going to be integration of from r equal to 0 for the ring which is smallest right at the center to the largest ring coming out to the circumference, because remember this radius is capital R. So small r, the radius of these thin disks, is going from 0 to capital R. So next step, this integration becomes very simple. 2m by capital R square is constant. We can bring it outside. So this is our next standard formula to remember. Moment of inertia of a thin disk about its symmetry axis. Okay, so we will come back to thin disk later again to also calculate moment of inertia about its diameter axis. But we will use a theorem for doing that rather than integration again. So the next integration example we will take
Sir,
is
1 minute.
Achha.
Done, sir.
Okay. Okay, so next example for us for moment of inertia, we will take the case of the hollow spherical shell. So this is now a spherical shell like this, but hollow from inside, so it's a thin crust.
Sir.
Yeah.
Sir, when we will do that case 2?
When we will do?
That case 2 of surface distribution.
This is surface distribution only now. The disk was also an example of surface distribution. This is also surface distribution.
No, axis along in diameter.
Yeah, we will do now. I told you, we'll do a theorem for that. We won't do by integration. First, we'll do the integration examples.
Okay, okay, sir.
So this is a thin uniform spherical shell. Its mass is m and radius is r. Now we want to find moment of inertia about any axis passing through its center. Okay. Any axis passing through the center of the sphere will be a diameter of it. So about the diameter axis. So we have to understand that this is also example of a surface distribution. So this is also a surface distribution. Okay. But the difference is this time that surface is a spherical surface. Okay. So it's an example of what we call a non-laminar surface or 3D surface. Whereas something like a disc or a rectangular plate is an example of a two-dimensional surface. It's a what we call a laminar surface. So anyways, sigma here will become m upon 4 pi r square. The surface area of a sphere we know is 4 pi r square. And it's a uniform spherical shell. So the mass is distributed uniformly over the surface. Okay, so again, we have to basically slice it into small areas and calculate moment of inertia by integrating. Okay, so if we take the vertical axis to the center as our axis of rotation, then we will have to take our surface element having the similar kind of symmetry about it. So we will slice as if we will slice using a plane which is parallel to the axis. So let's imagine this is our z axis. So let's take the origin of our system of coordinates as the center of the sphere. So center is at the origin. O, and the z axis is the axis of rotation. So then what we will do is we will slice thin rings like this using a plane which is parallel to the xy plane or perpendicular to the z axis. That is our differential element. So this is a thin ring. So the differential element dm, it is a thin ring in a plane perpendicular to the z-axis, perpendicular to the axis of rotation. You can see that you slice that using a plane which is parallel to the xy plane. So if this angle is theta now, then this small angle is d theta. Okay. And this thickness is r d theta. And this radius of the ring itself is capital R sine theta. So this thin ring, it is of radius r sine theta in my diagram, and of thickness r d theta. So it's of area against circumference into thickness. That becomes 2 pi r square sine theta d theta. So its mass sigma dA becomes, now substitute sigma from above, this one, this value of sigma that we've written earlier. So it will become capital M by 2 into sine theta d theta. So that is the mass of the disk. So just write down up to here first, then we'll proceed with the moment of inertia. So we got the mass of the thin ring in terms of its angular position theta and its angular thickness d theta. Okay. So
Sir, can we take that theta with respect to x-axis?
Can we determine the?
Can we take that theta with respect to x-axis?
Yeah, you can do that also. Only the way you take the limits will change.
Yes, sir.
Okay. So if you take with respect to x-axis, then my limit will be from minus 90 to plus 90. And I have taken from z-axis, so my limit will be from 0 to 180. But the final solution that you get for the integration will be the same. You're following?
Yes, sir.
Okay. So just note down up to here first. So as I said, we'll start today's session with the discussion. Okay, so now next thing, let's see, for that thin ring, the moment of inertia, that will become how much? That will become its mass into its radius square. Okay. So this is moment of inertia of the thin ring about the z-axis. So that is equal to dm, which is m by 2 sine theta d theta into its radius square. Now its radius is small r is capital R sine theta square. Okay. So now for the shell, for the spherical shell, the moment of inertia will become integration of this for all the rings. So it become integration of m by 2 capital R square sine cube theta d theta. Okay. And now visualize, I'm taking all the rings, the one at the top to the one at the bottom. So the one at the top is having theta equal to 0. And the bottommost one is having theta equal to pi or 180. So this covers all the rings from top to bottom. To answer your question again, if I had taken theta from the x-axis instead of from the z-axis, then my limits would be minus 90 to plus 90. But instead of sine theta, I would have got cos theta over there. So I would have got cos cube theta integration from minus to plus of 90 degrees. Here I'm getting sine cube theta integration from 0 to 180. So both will give me the same result finally. Now try to work out the integration of sine cube theta yourself. It's quite easy. I'll just give you a hint. Split sine cube into sine square into sine and express sine square as 1 minus cos square. Okay, so hope you must have got the answer. Let's complete this now. So for the integration, what we'll do is we'll express this as 1 minus cos squared theta into sine theta. And then we'll do a substitution here. So we will substitute cos theta as z. So minus sine theta d theta is equal to dz. So the moment of inertia by integration will become 1 minus z square into minus of dz from theta equal to 0 corresponding to z equal to 1 to theta equal to pi corresponding to z equal to minus 1. Okay. So we will get okay. So as you can see, when we put the limits, so this is the final important formula which you have to again memorize like the other standard formula. Moment of inertia of a thin shell about its diameter axis. Okay, so this is the case of the spherical shell. Now let's move to the final one of the standard derivations, which is moment of inertia for a solid sphere of uniform density. So same spherical shape as last time, but difference is this time the mass is fully distributed over its volume. It has a uniform density instead of the mass being at the surface. Solid sphere of mass m, radius r. It has uniform density. So it's a volume distribution of mass. And its density will become mass upon volume. Because we know that volume of a sphere is given by the formula 4 by 3 pi r cube. We had even seen the derivation of these formulae like surface area of sphere and volume of sphere by integration when we were doing that center of mass concept
Yes.
for hemisphere and all. Okay, so here we have two options. We can slice. Now, what about the axis? So again, we are taking the diameter axis. Any axis passing through the center will be a diameter axis. Now, to calculate moment of inertia, we have two options. We can slice it into disks, or we can also think of it like shells. No, layer after layer, like the layers of an onion. Okay, when you slice it, there are like of course an onion is not perfectly spherical, but they are shells which are one on top of the other. So you can think of this spherical mass also like having spherical shells which are thin and placed one on top of the other. So we can do that also, and we can make use of the formula of moment of inertia of shell that we have discussed just in the previous example. So again, any axis passing through the center is a diameter axis. So to calculate moment of inertia, we will go with the shell method. We will imagine that we are slicing this solid sphere into shells. Concentric thin shells. Of radius r and thickness dr. Now when you consider this shell about this axis which is passing through the center, this axis is a diameter to the shell also. Okay. So for this thin spherical shell, just a moment. Yeah. So for this thin spherical shell, of mass dm, radius r, thickness dr, the moment of inertia about this axis will be 2 by 3 dm into r square. Because this is what we just derived in the previous section. Moment of inertia of a shell is 2 by 3 mr square. So here it's a thin shell of mass dm. So it's 2 by 3 dm into its radius square. Okay. Now what about the dm? This thin shell's mass will become density into its volume. And the volume of the shell will become surface area into thickness. So dm will be replaced with density from above. 3m upon 4 pi r cube into its volume, which is surface area 4 pi r square into thickness dr. So that gives its mass as 3m upon capital R cube into r square dr. So that further makes its moment of inertia as 2 by 3 into this. So that will become 2 times m by r cube into r square. So that's r to the power 4 dr. So this is the moment of inertia of the thin spherical shell about this axis. So now from this we can see that moment of inertia for the solid sphere it is just summation by integration of moment of inertia of all these thin shells. So it is integration of 2 capital M upon r cube r to the power 4 dr from the smallest shell at the center, which is r equal to 0. It's like a dot to the largest center, largest sphere right at the surface of largest shell right at the outer surface of the sphere, capital R. Okay. And you can see everything except for small r is a constant. So there's a very easy integration at the end. It's an integration of r to the power 4 dr. So next step, you can just complete the integration and see what the answer will come for moment of inertia. So this is the final of the standard formula of moment of inertia that you have to memorize. Okay, rod, ring, disc, hollow spherical shell, and solid sphere. These are the standard moment of inertia values that you have to remember, apart from knowing the derivation technique also. So just write this down and complete the integration, people. Okay, people, so hope you must have got the answer 2 by 5 mr square.
Yes, sir.
Right, when you complete the integration. So these are the fundamental examples of moment of inertia. That is thin ring, thin rod, disc, thin spherical shell, and solid sphere that you have to remember as direct formulae. And then using these standard formulae along with some theorems that we're going to discuss next, we can calculate moment of inertia of more types of rigid bodies also. So hope all of you are clear with this example. So just to list out the standard formulae again.
Sir, can you scroll up once?
Sorry?
Can you scroll up, please?
Yeah. So hope you have worked out the steps of this integration also. Just write it out. 2m by capital R cube comes outside. That's how you'll get this finally.
Done, sir.
So let's just take a quick list of the formulae that we have developed before we move on to the next aspect of moment of inertia. Just a couple of important theorems. So thin uniform rod. So about the axis being the perpendicular bisector. Is ml square by 12. Perpendicular at one end. Ml square by 3. Okay. Then thin uniform ring. The symmetry axis. Mr square. Okay. Diameter axis. Mr square by 2. And thin uniform disc. Symmetry axis only. Mr square by 2. Then the spherical shell. Two by 3 Mr square. Okay. And finally, the solid sphere. So this is just for your reference in the notes. Okay, you have already seen the derivation of these examples before. 2 by 5 mRs. So as you get used to these standard formulae, we will also learn one more term related to moment of inertia, and that is called radius of gyration. So radius of gyration is a term that is used in context of moment of inertia. So radius of gyration is generally denoted with the symbol K, and moment of inertia of a rigid body is given by the formula mk square. So I being moment of inertia of a rigid body of mass m about a certain axis. So then the quantity K becomes the radius of gyration for that rigid body about that particular axis. With respect to the particular axis. Okay. So for example, here we can say that, for example, the radius of gyration for a solid sphere about its diameter is how much? So you can see that the moment of inertia, which should be mk square, is equal to 2 by 5 mrs. So from that we can see that the radius of gyration is square root of 2 by 5 times the radius of the sphere.
Sir, but what is radius of gyration?
This is the definition of radius of gyration, that it is defined as such a term which is having dimension of length such that the mass of the body into that radius of gyration square is the moment of inertia. The moment of inertia can be expressed as the total mass into k square. That is the definition of radius of gyration. Understood, no?
Yes, sir.
Okay. It has a significance that the larger the radius of gyration, the further away the mass is distributed from the axis, and accordingly the larger the moment of inertia. So for example, if you compare a thin shell with a solid sphere of same radius and same mass, but you see they have different radius of gyration. The thin shell has radius of gyration square root 2 by 3r. The solid sphere has radius of gyration square root 2 by 5r. So which one is having the larger radius of gyration? The spherical shell, the thin spherical shell, the hollow shell. That means its mass is distributed in such a way that it is further away from the axis. So the moment of inertia is larger. In that sense, there isn't too much difference between the term radius of gyration and moment of inertia. Is this radius of gyration is expressed in such a way that it comes independent of the mass. Okay, now let's come to.
Sir, 1 minute.
Okay.
What?
Okay, done.
No, sir. Done, sir.
Okay. So now next thing very important. There are a couple of important theorems related to moment of inertia. So the first one is called the parallel axis theorem. So let us understand the theorem first and its statement, then we will come to the proof of it. So basically, if we have any rigid body and we know the moment of inertia about some axis which is passing through its center of mass. So this is a rigid body of mass m and center of mass at the point C. So for this now, ICM is the moment of inertia about the axis through its center of mass. Okay. Now, if we consider an axis through any other point, that point could be within the rigid body, it could even be outside the rigid body, it doesn't matter. But if that axis is parallel to this one, okay, and the distance between these two parallel axes is d. So now, if the moment of inertia about another axis, okay, which is parallel to the axis about its center of mass, is given by the IP. Okay, then according to the statement of the theorem, IP will be equal to ICM plus MD square. Okay, where M we have already seen is the total mass of the body, and D is the perpendicular distance between the two axes shown. Okay. So just write down the statement of the theorem first, then we will come to applications, and then later we will see the proof also.
Sir, axis is perpendicular to the body, rigid body.
No, this is a three-dimensional rigid body, no, beta.
Okay.
It need not be laminar. You understanding the point?
Yes. Like solid
So just
sphere.
imagine, it's like a, like a randomly shaped rock or something. So the axis, both the axes are going through the rigid body. It can be laminar also, and in a laminar case, that the two axes should be mutually parallel to each other. Okay, and the first one, the one which we are writing ICM with, that should definitely be passing through the mass. We can't take any two random parallel axes and write this theorem. The first one must be passing through the center of mass, and the second one must be parallel to the first one. Then we can write the second one's moment of inertia as ICM plus MD square. Understood, huh?
Yes, sir.
Okay, so necessary and sufficient criterion for this theorem, that the two axes should be mutually parallel, and the ICM one, it must be passing through the center of mass. Okay, so let us see a simple example of its application. The first one that comes to mind is the case of the thin rod. So from integration, we have seen that moment of inertia about an axis passing through the center of mass and perpendicular to the rod is given by the formula ml square by 12. So we have a thin uniform rod of mass m and length L, then moment of inertia about an axis through the center of mass and perpendicular to it is like this. Okay. So now if we consider any axis which is at a distance d like this over here and parallel to this one, this should become ml square by 12 plus md square. And additionally, for d equal to L by 2, P is at the end of the rod. And it will just prove the formula that we have already got by integration earlier. That when we substitute d as L by 2, we will get ml square by 3. So even in the case of the rod now, you don't need to memorize the formula for the moment of inertia about the end. You can just memorize the standard formula for moment of inertia about the center axis and then use parallel axis theorem, taking the distance d as L by 2. Okay, so let's do a couple of more examples. So find the moment of inertia for a thin disk about an axis passing through a point on its outer circumference and perpendicular to its plane. So basically, consider this like your disk, and now this is the axis of rotation, like this. Or if you consider a two-dimensional diagram, you're looking into the disk front on, and your axis of rotation is right over here, coming out of the plane. The rotation is happening about this axis. Mass of the disk is m and radius is r. Please work it out and send me the answer. It's very simple, direct application of formula. Okay, very good. That's correct. 3 by 2 mr square. Jay and Harsh. So you can see here that you have to just draw an axis which is parallel to this one and passing through the center of mass. And then just use this theorem that this particular axis we want to find. So here D is equal to R and ICM we have just seen for the disk. This, so we'll get 3 by 2 mr square. Now let's see a more detailed sort of application example to wind up. So now let's take a dumbbell shaped body, okay, which consists of two solid spheres, okay, connected by a thin but heavy rod. So typically an actual dumbbell will have a pretty thick rod, but here we will consider the rod to be thin, at least relatively thin. So these are identical solid spheres of mass 2 kg each and radius equal to 50 centimeters each. Okay. And this joining them is a thin uniform rod. Now this has mass equal to 1 kg and a length equal to, let us say, 2 meters. Okay. Now the length is from circumference to circumference. Okay, so this thing is the length, not from center to center. Now we have to find this whole system's moment of inertia about this axis passing through the center of the rod and perpendicular to it. This is a dumbbell shaped body. It consists of these two solid spheres joined by a thin uniform rod. So we have to find moment of inertia about this axis. So moment of inertia will be moment of inertia of sphere 1 plus moment of inertia of sphere 2 plus moment of inertia of the rod. Okay, you can divide the rigid body into 3 individual bodies. Okay. And now each of these you calculate by using the parallel axis theorem. And for this use the standard formula. Just try this out quickly.
Sir, it is a solid sphere.
Yeah, both the spheres are solid. Okay, so got the answer, people. So see, each of the spheres, they will give you the same value of moment of inertia about the given axis, because for each of the spheres you are at a particular same distance from the axis, right? So whether you consider this sphere or the other one, this center point where the axis is there. Now this, remember, is not the center of mass of the sphere itself. The center of mass of the sphere is this one. So this perpendicular distance d will become how much? It will become capital R plus L by 2. Okay. So for each sphere, the moment of inertia about the center of mass axis is 2 by 5 mr square. So the moment of inertia about this new axis, which I'll write as C only, but that C is not center of mass, it is a different point with respect to the sphere. So this is going to be this. Okay. So here D is equal to L by 2 plus R. So let's calculate this. So now let's use the values that are given to us. Okay. So 2 by 5 into mass of each sphere is 2 kgs into radius, which is 0.5 meters squared, plus 2 into this will become how much? 0.5 plus half of 1, so 1.5. Like this. This is 4 into 0.25 divided by 5 plus 2 into 1.5 squared, 2.25. So this is going to be 0.5 plus कितना हो जाएगा 4.5. So 5 kg meter square. This is for each sphere. This is for each sphere. And moment of inertia of the rod is very simple. Directly use the formula ml square by 12. So even the other sphere is in the same kind of position. It's at the same distance d and all that. So same mass, same radius, same everything. So each sphere has this much. Now moment of inertia of the rod, it just becomes its mass into L square by 12. So mass of the rod was how much? 1 kg. Okay. Multiplied by its length was 2 meters. So that's becoming 4 by 12 or 1 by 3 or 0.33 kg meter square. So the moment of inertia of the whole rigid body is 2 times moment of inertia of each sphere plus moment of inertia of the rod. So you will understand here that even though they are of similar kind of mass, the rod is 1 kg, the spheres are just double of that mass. But the moment of inertia of the spheres is much larger because of the distance factor. So this ultimately becomes 10.33 kgs meter square. Okay. So this is a typical example of how we have to make use of the combination of standard formula and theorems for calculating moment of inertia of any general kind of rigid body that is consisting of various shapes connected together.
Sir, so we have to first split all the rigid bodies.
Sorry, we have to
Split all the shapes.
Yeah, we have to split. Jay, which one you are saying should be 4.7? I see about this one. It should be 4.7, is it? We just check. 2 by 5 mr square. M is 2, this is 0.5, so that's all right. Plus 2 into d square. Now d will become how much? 1 meter plus 0.5. So 1.5 is correct. 4.5 plus. Oh yes, my mistake. Yes. Wait a minute, people. There is a error here. This should not be 0.5. No, this is 1 by 5. So this should be 0.2. Just make a small correction here. This first term should be 0.2. Okay. So this will become 4.7. Yes, thanks for pointing that out, Jay. Okay, so now this final answer will change. Okay. Become twice of 4.7, so that is 9.4 plus 0.33. So it will become 9.73. Is that correct, Jay? Okay, good. Okay, so people, make sure you've noted down this correction here. This was a calculation mistake on my part. It's 1 by 5 here, so this should be 0.2. So that's why this moment of inertia is 4.7 for each sphere. And this one is correct. So finally, replace this with 4.7 and this with 0.33. You will get this answer. Okay, so next time we will continue ahead. We will see the second theorem of moment of inertia called perpendicular axis theorem. We will also take a brief look at the proof of each of those theorems. But we'll see more importantly that using the theorem and the 5 or 6 standard formulae, we can calculate moment of inertia of all these types of rigid bodies that consist of standard shapes. So that's it for today's session, people. Wish you all the best. Thanks for attending.
Thank you, sir. Bye, sir.
Thank you, sir. Bye, sir.
Okay, bye, people.